Hey guys, welcome to the stereochemistry part of the Diels-Alder videos. So in the previous videos, we talked about how orbitals come into play in the Diels-Alder reaction. And we talked about regiochemistry. Now we're going to have to talk about the stereochemistry. Remember, we completely excluded all stereochemistry from the answers that we did in the previous practice videos, but on the test, you will have to take into account stereochemistry. All right, I only talked strictly about regiochemistry just to get you guys used to it. All right. Now we got to talk about the stereochemistry. So I'm going to focus on it by parts, focusing on the diene and then focusing on the dienophile. You can see in this example I drew the regular old 1,3-butadiene, and we have this weird looking dienophile. Alright? So let's look at this dienophile. Let's just make sure that those are electron withdrawing groups. Look at the resonance. Alright, so it doesn't matter if you want to involve this guy in the resonance or this guy, they're the same substituent, so we can pick either one. So I'm going to resonate him up, bring that double bond up, and our resonance structure is going to look like this. The positive charge on this carbon, if we resonated this guy the other way, we're going to get this structure. Alright, so the partial positive is either on the top carbon or the bottom carbon. Doesn't matter, this molecule is symmetrical. Alright, so we don't need to worry about that. So we just confirmed that those are electron withdrawing groups. Alright, so now we have two electron withdrawing groups on this compound. And if we look at it, let's see, is it cis or trans? Split this double bond down the middle. If you look at the left side, this carbon, part of the double bond, has a hydrogen here, and so does that one at the other side. Now, the priority group on the top side of the double bond, the highest priority group, is going to be this substituent. So going in the upwards direction, or to the top right direction. Looking at the bottom half of the double bond, it's going this way. And so that's cis. Okay, so we have a cis dienophile. The trans version of this dienophile would look like this. That would be the trans version. If we split the double bond down the middle, this is coming upwards, this is coming downwards, you can see that they're on the opposite side of each other. The higher priority groups on the opposite side of each other. So we have our cis dienophile and we have our trans dienophile. So how is this reaction going to look if I use both of these dienophiles? So let's go through each one. So first, let's just focus on the cis version. Alright. So let's draw our Diels-Alder arrows. This double bond attacks that carbon. This comes down. And that one flips upward. And number your carbons. 1, 2, 3, 4, 5, 6. Now there isn't any electron donating groups on our diene, so we don't really need to worry about anything in terms of regiochemistry. It's going to be pretty straightforward. Draw the 6-membered ring. 1, 2, 3, 4, 5, 6. Alright. The double bond is going to be between 2 and 3. Now, on carbon 6, we had our carboxylic acid, and on carbon 5, we also had it. Okay. Now, the way I like to approach any problems requiring stereochemistry in Diels-Alder, I always leave it till the end. What that means is I draw everything planar, and then worry about the wedges and dashes later. Okay. So, what is this going to look like now, right? We drew the planar versions. That's the regiochemistry is all done. But what about the stereochemistry, right? How is this going to look now? Well, this is the thing that we talked about. This is why I brought up the fact that there's a cis and a trans version. When you have this cis dienophile, those two high priority groups always have the same stereochemistry. In trans, they are opposite, right? Should be pretty straightforward. So in cis, the electron withdrawing groups are the same stereochemistry, and on the trans compound, they are opposite. So we drew everything planar, so now let's redraw, but with stereochem. So we have to give stereochemistry to this bond and that bond. All right. And the way we would do that is we make them either both wedged or both dashed, up to you which one you want to do. Let me make that a little bit better. I made them both wedged. Like this, right? And remember, there's only going to be one product in this case, because if we drew the dashed version, right? These two compounds are identical to each other. All you need to do is flip the molecule, all right? So they're the same, one product. So that's what happens when you have that cis dienophile. Let's look at the trans version, all right? So here's our trans dienophile, same diene, our arrows, a little bit sloppy, but I'm sure you guys should be okay with the arrows by now. Number 1, 2, 3, 4, 5, 6, 6-member ring. Ring number 1, 2, 3, 4, 5, 6. Double bond is going to be between 2 and 3. Now remember, like I said, I like to draw everything planar and worry about stereochemistry at the end. Right? So you see that the planar version of the products are the same, right? So now let's do the stereochem. We said that in the cis, the electron withdrawing groups are the same stereochemistry, right? We drew them both wedged or both dashed, but these are the same product in the end. For the trans version, they're both opposite, all right? So that means one will be wedged, one will be dashed. So let's withdraw what that's going to look like. So let's make the top bond wedged arbitrarily. That means the bottom one will now have to be dashed. Okay, we can draw the other version. Okay, and these are going to be enantiomers of each other. So in this case, we do have two products. If you try to take, let's say, this guy, and you flip him, you're not going to be able to overlap him onto the guy on the left, because this bond, when you flip it, will be at the top now, and it will be dashed. Oh, my mistake. And this guy, when you flip him, will be at the bottom, and he's going to be wedged, all right? And so in this case, we have two enantiomers of products, but the main point I want to get across is how we have these two bonds are opposite stereochem. All right, whereas because that's of the trans dienophile, the cis dienophile, we have these as the same. Okay, so that's when we have the dienophile. Hopefully that shouldn't be too bad. Now let's talk about our diene. Right? This one is a little bit more tricky. Hopefully not too bad. And then we're going to get to examples where we combine them. So let's see. I'm going to draw one diene that looks like this now. And I'm going to do the regular plain old ethylene dienophile. That way we don't have to focus on that. We can focus on one thing at a time. And later on we'll combine diene and dienophile. So, with the diene, it's a little bit more tricky, but there's a good little guide in terms of the cis and the trans versions, all right? I'll go through first how we can figure it out, and then I'll show you the trick, but again, it's always good to know how we can actually figure it out. Split this one double bond down the middle. You have an H over there, and an H over there. Okay? So, looking at this double bond alone, so we're not focusing on this part of the diene, just the double bond at the top. All right? If you see that our highest priority group near the right-hand side is going to be that methyl pointed upwards. The highest priority group on the other end of the double bond is this group. So you see they go opposite directions. So this is that methyl is trans. All right? That methyl is going to be trans. And the same thing if we do it over here. We're going to have an H there, H here. That's your highest priority group on that side of the double bond. Here's your highest priority group over there. So when I say that they're trans, I'm saying that this methyl, in relation to strictly the rest of the diene, this is trans. But like we did for the dienophile, we want to look at those two electron withdrawing groups. Like we looked at those two electron withdrawing groups together. If they're both the same, facing the same side, they have the same stereochem. If they're opposite, they had opposite stereochemistry. In this case, that methyl, those methyls are on the same side of each other. They're both trans to the rest of the diene. And this little guide I was telling you about that can help you figure it out a little bit easier, and it's a good idea to put this on your index card, is this. Here's your diene. The group that's going to be this way is going to be trans. All right. Any two groups that point out to the side like that are trans. If they point inward like this, they're cis. And any two groups over here, they have no stereochemistry, because remember, at the end of the Diels Alder, we get a double bond right there. So any two bonds coming out of there will not have any stereochem. So we're just going to put M. Alright, so keep this little guide in the back of your head, right, because it could definitely come in handy. Now, also before we keep going, one thing that's good to keep in mind is oftentimes they will give you the S-trans conformation of the diene, right, because they want to see if you know how to rotate the bond. How this would look like in the S-cis conformation, so the S-trans conformation, this is S-cis, would look something like this. Here's your diene. So the trans substituents, let me keep that consistent, put that in red, would be these guys. The cis would be this one, and it would be this one. And the ones we labeled as M with no stereochem would be those. So that's S trans. I find it more helpful just to know the S-cis version, right, and just get comfortable with bond rotations, all right? It's a good idea. It's a good habit to get into, and it comes in handy. So I'm just going to keep the S-cis version for now. So because these two methyls are both trans, right? They're both going to be the same stereochem. Do not get confused just because I'm calling them trans. That doesn't mean they have opposite stereochemistry. What the trans means is in relation to that double bond and that double bond. But between each other, comparing them to each other, they're the same. So let's draw our arrows. And so our 6-member ring, and let's number actually 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbons 2 and 3 get that double bond. We had our methyls are 1 and 4. All right, let me just clean up the numbering a little bit. So we drew the planar versions, and now let's focus on the stereochem. All right, they're supposed to have the same exact stereochemistry, either both trans or both wedged. Sorry, both wedged or both dashed. So let's draw that. Let's just make them both wedged. We can draw it this way, both wedged, or both dashed. Now again, like in the case of the Dienophile, when they were both cis, in this case we only have one. Oh, yeah, in this case we only have one product, all right? Because I can take him, flip him, and he's going to look exactly like this. So we have one product in this case. But the main point I'm trying to get across is how when you have the substituents like this, going in these opposite directions, they'll have the same stereochemistry, right? They're both trans in terms of the double bonds they're on, but relative to each other, they're the same stereochem. Okay? Now let's talk about if we had a diene in which it would be the opposite of what we just covered. So what I'm going to do is I'm going to just change this methyl, and I'm going to point him inward. And actually, I erased the previous little guide, so let me just redraw that. So now in this case, one of these methyls is pointed in that trans position right here. This methyl is pointed inward. It's in that cis position. Now, one thing I just want to keep you guys to keep in mind. Remember that these carbons with that diene, the carbons at the end of that diene, so right here and right here, they have hydrogens on them. Okay. So in this case, this hydrogen is pointed in that cis version inward. This one is pointed in that trans outward. All right. So we're going to react it again with this regular ethylene. And what is our product? Draw that 6-membered ring. Renumber 1, 2, 3, 4, 5, 6. Carbons 1 and 4 had those methyls. 2 and 3 gets that double bond. So here's the planar version. Now let's draw it with stereochemistry. All right. In this case, because this methyl right here, let me just change the color. This methyl off carbon 1 is trans. the methyl off carbon 4 is cis. Because they're not the same, and either both trans or both cis, they have opposite stereochem. So one will be wedged, one will be dashed. So let's draw this guy wedged, this guy dashed. Draw the other version. And in this case, we have two separate products, enantiomers of each other. You can take this guy, flip him up 180 degrees, and you will not be able to get it to overlap onto that guy. This methyl that's wedged is pointed downward. Remember, that means it's coming at you. If we flip it upwards 180 degrees, it's now going to be pointed up, but away from you. That's dashed. Whereas if we wanted it to be up and towards you, wedged. So we're going to get two enantiomers as our products. So this is how the stereochemistry plays into effect in terms of strictly looking at the diene and then the dienophile. In the next video, we're going to look at what happens when we combine the two. So we're going to have cases where we have stereochemistry on the diene and then the stereochemistry on the dienophile in the same example. All right, just do what you guys have been doing now. Take it one step at a time. Hopefully, it will not be too bad. All right, I'll see you guys in the next video.